Welcome to this explainer. Today, we're decoding a frankly brilliant architectural breakthrough that is solving one of AI's absolute biggest physical bottlenecks. If you've been following large language models lately, you already know the deal. Memory, specifically the sheer amount of context a model can juggle at once, is literally the ultimate frontier. We are looking at a fascinating paper straight from the team at MiniMax, and they've introduced a ridiculously elegant solution to this exact problem. So let's dive right into the multi-million-dollar question sitting at the absolute bleeding edge of AI scaling today. How on earth does a model read a million words all at once? Well, historically, the short answer has been with incredible difficulty and at a computational cost that would make your eyes water. But as we're going to see, that entire paradigm is shifting in a big way. Here is our roadmap for today. We're going to hit the ultra-long context challenge, unpack the quadratic bottleneck, and then enter MiniMax Sparse Attention. From there, we'll break down their two-branch system, dig into the software and hardware co-design, and finally, look at the massive speedups at scale. Let's get into it. Kicking things off with Section 1, the ultra-long context challenge. You see, today's AI models are no longer just glorified chatbots spitting out a quick paragraph. We're asking them to act as autonomous agents. Developers want these models to handle complex, long-horizon workflows, reason across entire massive code repositories, navigate the open web, and keep a persistent memory alive across hundreds of different user sessions. To actually pull that off, a model needs to hold hundreds of thousands, if not millions, of tokens in its active memory at the exact same time. The demand is absolutely there, but honestly, the physical reality of computing has been holding us back. Which brings us to Section 2, the quadratic bottleneck. So here is the main villain of our story. Standard LLMs rely on a mechanism called softmax attention. What this means is the model has to compare every single new word, every token, against every single previous token just to figure out what's important. Because of this, the computational cost grows quadratically. And that's the kicker. If you double the context length, you aren't just doubling the cost, you're quadrupling it. Trying to push that to 1 million tokens creates an impossible physical bottleneck for any real-world production-scale deployment. I mean, it literally breaks the server budget. There's just no way around it. But thankfully, there is a fix. Section 3. Enter MiniMax Sparse Attention. Notice the massive shift in philosophy here. Traditional dense attention is kind of stubborn, right? It reads every single token every single time. Yes, it's highly accurate, but it is computationally crushing at scale. MiniMax Sparse Attention, or MSA, totally flips this. Instead of forcing the AI to painstakingly read every single word for every single query, MSA intelligently skips the noise to focus purely on the signal. It cherry-picks and reads only the most relevant blocks of information, which makes it dramatically faster and infinitely more scalable. Let's see how they actually pull this off in Section 4, the two-branch system. This setup brilliantly captures the elegance of the whole system. What we're looking at is an intentional splitting of the cognitive workload into two very distinct paths. On one side, we have the lightweight index branch, and on the other, the heavy-lifting main branch. By separating the task of searching for the right information from the task of actually reading it, MSA totally bypasses that nasty quadratic scaling problem we talked about earlier. Let's break down how this works step by step, because it's pretty clever. Think of the index branch in Step 1 as a lightweight scout. Its only job is to rapidly sprint through a massive library, skimming the shelves to find the right books. It scores blocks of text and selects what's called a top case subset, basically flagging, hey, the answers you need are in these specific blocks. Then Step 2 kicks in and the main branch takes over. Think of this branch as the deep reader. It doesn't bother looking at the whole library. It exclusively and intensely studies only those chosen text handed over by the scout. Of course, theory is just theory. Moving on to Section 5, software and hardware co-design. I absolutely love this quote from the source material because it hits on a really harsh reality in AI development. You can dream up the most efficient algorithm in the world on a whiteboard, but if the physical GPU hardware isn't optimized to actually execute it, you are not going to see any real speedups. The MiniMax researchers totally recognize this. They knew the MSA algorithm and the physical GPU hardware instructions had to be intentionally co-designed to speak the exact same language. So, what did they actually do under the hood at the hardware level? Well, they built highly specialized custom instructions, or kernels, right into the GPU.
For example, they created an exp-free top case selection. Since the Scout branch really just needs to rank blocks to find the top ones, this kernel completely skips the heavy, unnecessary exponent math that standard softmax requires. They also reorganized the attention processing using a KV outer approach, which perfectly maximizes how those GPU tensor cores want to ingest data. Oh, and to prevent major traffic jams when multiple queries all try to read the same popular block of text at once, they instituted pre-scheduled chunking. It is just incredibly tight, brilliant engineering.
Which brings us to the results. Section 6, massive speedups at scale. Now, the MiniMax team didn't just test this out on some tiny little toy model in a lab somewhere. No way. They deployed it on a 109 billion parameter mixture of experts behemoth, and they natively trained it from the ground up on a massive 3 trillion token budget. And what's really crucial here, this wasn't just text. This model was trained across text, images, and video data.
And here's the number that completely changes the game: 28.4x. By limiting the attention budget to a fixed number of key value tokens, thanks to that Scout branch we just talked about, MSA reduces the per token attention computation by a staggering 28.4 times at a 1 million token context limit. I mean, that is just a massive reduction in the raw math the computer has to process. But as we know, raw math reductions don't always translate perfectly to physical time saved. So looking at the actual wall clock speeds measured on high-end H800 GPUs, we can see the real-world impact. Compared to a heavy, dense baseline, MSA achieves a massive 14.2x speedup in the prefilling stage. That's when the model is initially reading your giant prompt. Plus, it gets a 7.6x speedup during the decoding stage, which is when it's actively generating its response back to you. Now, the absolute elephant in the room is, does making the model skip reading every single word actually make it dumber? Well, crucially, as this condensed benchmark data proves, the answer is a hard no. These incredible hardware speedups do not sacrifice model intelligence whatsoever. If you look at the numbers comparing full attention to the sparse model, it's pretty clear. Whether we're talking general reasoning on MMLU, math on GSM-8K, coding on human eval, or even image tasks like ChartQA, the sparse MSA model performs totally on par, and in a few cases even slightly better than the resource-heavy dense baseline. It is a complete win-win. And what's really fantastic for the broader developer community is just how accessible this is. You've got 2 deployment routes, giving you ultimate flexibility. You can choose to train a model natively from scratch with this sparse architecture from day one. Or, and this is wild, if you've already spent millions training a traditional dense model, you can practically hot swap MSA right into your existing checkpoint, with just a short warm-up training phase. It offers a near-lossless conversion. Which brings us to our final thought. With the computational cost barrier of ultra-long context finally shattered by MiniMax Sparse Attention, the fundamental physics of what we can afford to run have changed. If holding millions of tokens in active memory is suddenly efficient and cheap, what kind of incredible autonomous applications and agentic workflows are developers going to build next? The bottleneck is broken, folks. The next phase of AI scaling is officially here. Thanks for joining me on this explainer, and we'll see you next time.